Yo, what's up, guys? Today, it's been a long time. As you can see, I have actually received this question from Vibing Map. Actually, it's a very old question, and yet it's very interesting. As you can see, it is a modified Olympiad maths question, and it has to do with bits of the vector. And I think like your as the A levels or A levels pure math paper 3 CIE A level students, or those who actually studied a bit of about further maths, they might be able to do so. So why don't you give a try, and we will come back in few minutes. Okay, so you might have paused the video and tried, and I assume that some of you might have a correct answer, some of you might not, and I will try to review the answer. So the shortest distance between these skew diagonals is actually 1 over the square root of 1 over 3, okay, which is this one. So I'm gonna tell how you get this answer. You have two skew vectors. The diagonals of they are actually the diagonals of one side of the cube, as you can see. So you have here, these are the two vectors I can say. Now you have R1 and you have R2. And we know that we can actually just try to make our own vector in a very simple way. Just try to imagine that this is your z-axis and this is your x-axis, and this will be your y-axis. So we treat these every single axis as a positive axis, okay? And what we're gonna do is we need to find the coordinates of each single, these 4 points. So I want to say this one, of course, is the origin, is 0, 0, 0. And this one will be, in this case, because we have not moved the point along the y, this y-axis, and hence we have only a and then 0 and then a. Okay, it makes sense, right? It should make sense. Okay, this one. So how about this one? You can actually have 0, 0, a, because you have not moved the point along the x and the y-axis. And this one definitely is a, a. And we know that in this question, the unit cube is used. So what is meant by unit cube? Unit cube means the side length of the cube is 1. Okay, so we must actually recognize that this length must be 1, and this length must be 1 too. And also, this length, every single length of a cube, it must be 1. And you notice that we have moved along the xyz axis, which they are actually parallel to, they just actually lie on the cubes, on the side of the cube. So we just actually try to rewrite them in terms of the numbers, just the numbers of 1 here, and then this is also 1, and then we also write 1, 1, 1 at here. Okay, but this is the answer. We just erase it for solving purposes. So we have these points, and we can actually find the direction of vector. Because we have 2 points, then we can actually use the fact that, for example, R1, the direction of R1 is nothing but the differences between these 2 points. Okay, between these 2 vectors, I can say. So it's 101 minus 0, 0, 0. And then we will have a 101 here. And then for R2, the direction will be at the same, will be 1, 1, 0. Okay, if you use the same method. And it's not enough to just have the direction vector. We must also have just like a equation of the straight line, we must have an equation, the vector equation. So we have to use any, for example, I want to parameterize that R1 in terms of x. So x, it must be attached to the direction of the vector, which is the 101. So you can just say 101x and then plus any starting point of the vector. So R1 has the starting point of 0, 0, 0. So just write. Okay. Why do I actually choose 0, 0, 0? Because you try to substitute x equals to 0. When x equals to 0, the vector is just 0, 0, 0. Because 0 times the 101, the vector itself is 0. So we just have left 0, 0, 0, this remaining vector here, which is true because the vector doesn't move at all at the origin. So for R2, we also have y. Well, in terms of y, and the direction vector again is 1, 1, 0, y, and then plus the starting point, which is 0, 0, 1. So we can actually write in single vector like so, which is this one is x, this one is 0, and this one is x. And then this one equals to, in this case, this will be y, this will be y, and then this will be 1. Okay, that's just a task that we want to do. Okay, it's simple right now. Yeah, obviously, but we have multivariables, so it's okay, no problems, no worries. We can just actually see the question again. So we need to find the shortest distance between two skew diagonals. So the shortest distance, it gives me two important things. First and foremost, two vectors R2 and R1, they must be perpendicular to that line, which is this one. We label this, we name this as whatever, I will call it as R3. So R3 is this line which passes through two skew diagonals via these 2 points. And R3 itself, it is perpendicular to R2 and also to R1, or orthogonal. And then R3 is the shortest distance, so we can just use the fact that R2 minus R1, the modulus of the R2 minus R1, the distance is the shortest, and we can use the total differential equation to solve and somehow derive the relationship between x and y. So let me show you what I mean actually. So we know that we can use the distance formula by, just try to find these this vector difference between R1 and R2. And what we will get is actually the R3. We can take R3 in terms of x, y, okay, is also essentially the difference between the vector R1 minus R2y. Just try to express it into the single vector, and then hence not only you will have this one, because of negative numbers, so I would rather say that this is R2y minus R1x. This will be better. Yep. Okay. This will be somehow convincing. And then what we have right now is just the single vector of R3 in terms of x and y. We do not know what x and y are, but we must know what is the relationship. We are able to derive the relationship between x and y. So how? We know that the distance of R3 itself is nothing but the square root of y minus x squared plus y squared, and then plus the entire expression y minus x squared, which is this one. And then we can just simply write the distance as d in this case, for convenient purposes. So we can just move that d, we can just move that square root to the d there, and the d will become the d squared, and then the remaining expression will be free of the square root. So, yep, it's right now like this. And we try to differentiate for each d. It's just like, well, somehow like a total differential equation. So how we actually deal with this? So we know that we can try to differentiate with d by moving the 2 and then minus the 2 with 1, and then we will get 2d. And then with the chain rule, we have to d prime. We have to include the d prime, okay, and multiply it with the 2d. And then on the right hand side, you must also differentiate in multivariables way. So we have to try to differentiate in respect to x at first. So any term with x must be differentiated accordingly. So in this case, we differentiate with this one first. So we will have 2 y minus x, and then this will be 1. And then with respect to x, we must also apply the chain rule. In the y minus x, we will have minus 1. Okay, so remember, we treat x as a variable and then y as a constant in this case. So the y squared must be 0 when we differentiate in respect to x, because y squared is a constant. And then 1 minus x, this entire thing, will become 2, and then 1 minus x, and then here, inclusive of the chain rule, and then that's all. And then we differentiate in respect to y. It's the same thing, just we have to treat y as a variable while x as a constant. So 2 y minus x, and then nothing happens because when you differentiate y, you will get 1. So we don't have to write 1. And then we can finally differentiate y squared by having 2y, and then 1 minus x squared, the entire thing is just x. So x is a constant, so 1 minus x, when you differentiate, you will get 0. So you have 2 yx minus 1, and then you have here 2y minus x. This implies that we can cancel these two things out. So we will have, and one more thing, because we want to find the shortest distance in differentiation. What is the use of differentiating? Well, each variable, because we can actually find the maximum and the minima. So the maxima and the minima of the distance, when you differentiate the d here, you must have also the d prime as a 0, because it's just like, well, when you find the area in terms of x, when you differentiate d, okay, differentiate the area in respect to x, this one will be equal to 0. Imagine that a is also a distance, while x, y are also the variables. You differentiate the distance in respect to x and also in respect to y, your d prime itself will also equal to 0. Okay, this is just a quick concept. Now, this thing is turning into 0 right now here. And then we have these remaining two terms here. Okay, we have 2y, okay, and then minus 2. 1 minus x is very fast. And then we can get just a simply 1 minus x equals to y. We have a direct relationship, a linear relationship between x and y like this. As you can see, x and y, they are the values which must be less than 1. It's obvious. And you'll be surprised by the fact that x and y are just 1/3 or maybe 2/3. So this is just the direct relation. We just have derived the relationship between x and y. So we need to find x and y. How? So we can actually recall back the fact that the orthogonality between the vector r3 and r2, or maybe between the vector R3 and R1, we choose, well, let's say we choose the orthogonal between R3 and R1. So recall back, R1 is nothing but 101, and then R3 is this entire thing. So we can actually just remember, if R3 is orthogonal to R1, then the scalar, the dot product of R3 and R1 must be equal to 0. Or we can do the same thing between R3 and R2, but in this case we try to do R3 and R1. So R3 is nothing but y minus x, y 1 minus x, and then dot with 101 here. This is equals to 0. Okay, now we can just try to, just like usual, and we will have these things here. Okay, now we try to express y in terms of x. We just substitute this one into this equation, and eventually you will get this one, which is 1 minus x, and then minus x plus 1 minus x equals to 0. So we realize that 1 plus 1 is 2, and then minus x minus x minus x will becomes 3, and then x equals to 2 over 3. This is the 2/3. So y must be equal to 1 minus 2 over 3, which is equivalent to 1 over 3. Well, it's nice. So can we find the shortest distance between the two vectors? Yes, we can, because we have a R3 here, and we have already derived this distance formula here. Copy, okay, this one, the distance formula, remember this one, this is the distance formula. Okay, now we just have to find the d, and that's the answer. So we can just substitute first the y equals to 1 over 3, and then this one is 2 over 3, and then square 1 over 3 square plus 1 minus 2 over 3 square. You will get here will be 1 over 3 square, and then plus 1 over 3 square plus 1 over 3 square, and then this equals to 3 times 1 over 3 square, and then this equals to 3 over 9 equals to 1 over 3, and then d equals to square root of 1 over 3, and then QED. Okay, now I would like to recall back our strategies that we have done. We have executed perfectly. And now, the first thing I know is we can actually use the vector method to somehow find the relationship between the vectors R2 and then R1 and R2. And then we have to identify that this R3 vector is not only orthogonal to R2 and R1, but also it's the shortest distance between two vectors R1 and R2. So it's very important. Short distance obviously means that the orthogonality. It also means that we can use the differentiation, which is the multivariable differentiation, which is this one. You might find very hard to understand this thing, but you might learn this in calculus 2, no, in calculus 3, which you have to learn multivariable calculus. And somehow I have taught you the very important technique when you deal with differentiating multivariables. When you deal with this total differential equation, this thingy, when you differentiate them, you have to remember that you have to treat only one of the variables as the variable, while the rest must be the constant. If you have, for example, x, y, z, you have to differentiate in respect to x. So you must treat x, y, and z as the constants. And if you differentiate in respect to y, so you must treat x and z as the constants, obviously. So after I have done the total differential equation, I have produced the relationship between the x and y, which is 1 minus x equals to y. And then I use the fact that the dot product equals to 0 because of the orthogonality. And then I have somehow get a linear relationship between y and x, which is this one. And then I substitute y in terms of x, this one, into the equation. And then I get x equals to 2 over 3, y equals to 2 over 3. When I plug in the x equals to 2 over 3 in this equation. And I finally get the distance. I just plug everything, x and y, and then I will get d, the shortest distance, equals to the square root 1 over 3. Thanks.